Let's continue to see the properties of power series. Okay, here is the second part. Differentiation of power series. Let's see theorem 2. Power series 1 can be differentiated term by term. That is, at each point G, interior to the circle of convergence of that series, S prime of G is equal to summation n is equal to 1 to infinity n times a n times G negative G naught to the n negative 1. Okay, let's prove this theorem. Let G denote any point interior to the circle of convergence of series 1. This is series 1. Then let's see be some positively oriented simple closed contour surrounding G and interior to that circle. Let us also define the function G of S is equal to 1 over 2 pi I times 1 over S negative G to the G squared at each point S on the contour C. Okay, it is easy to see that G of S is continuous on C. Theorem 1 tells us that this equality holds. Integral along the contour C, Gs times S of S ds, because Gs is continuous on C, we can apply theorem 1, which is equal to summation n is equal to 1 to infinity an times integral C Gs times G negative G naught to the n ds. Now, G of S of G is analytic inside and on the contour C, and so we can write this integral along to contour C Gs S of S ds, because Gs is defined by this 1 over 2 pi I times 1 over S of S negative G square. So this part Gs is replaced by this definition. Then we get this. Then we know that integral representation for derivative in section 55. So this is exactly the S prime of G. Also, we have this integral along to the contour C, Gs times S negative G naught to the n ds. Okay, here Gs is, as I mentioned, given by this form. So replace it. Then we get this. Then we have this d over d dg G negative G naught to the n. So this is actually in the previous equality, I mean expression 9, this. this. So this part can be replaced by this. And we just have this result. So on the left hand side, S prime of G, yeah, it can be placed here. Then here, S prime G is equal to this expression, which is summation n is equal to 0 to infinity an times, yeah, this d over dg g negative g naught to the n, okay, which is exactly the same to expression 6 in the theorem 2 here. So we complete the proof. Okay, let's look at example 2. So to understand what the theorem says. Here in example 1, in section 64, okay, we saw that 1 over g is equal to summation n is equal to 1 equal to 0 to infinity negative 1 to the n times g negative 1 to the n, where absolute value of g negative 1 is less than 1. This expression holds. Differentiation of each side of this equation. Then we have this. We have differentiation of this function g over g here, negative 1 over g squared is equal to this part when we have differentiate. We differentiate this part, then we get this, because this is a polynomial. So n times g negative 1 to the n negative 1, here we get this. Or we drop the sign here, or multiplied by negative 1 to each side of this equation, then we get this.